Okay, hello everyone in a new video. Then we have reached part 5 of chapter 9, which is the chapter of equilibrium of a body in the third unit of mechanics. And we have reached the final section, which is section number 18, and it's given by the principle of interaction. Then let me write down the title of this section. So what is meant by the principle of interaction? Now, before I state this principle, let me give an overall picture of this principle. So first of all, we need two bodies that are involved. So what are the two easiest bodies that we can consider? Is, for example, suppose that we have a support which is a table, and on this table we will place a solid S. So let me place the solid. So first of all, we can say that because the solid has a mass, it will be subjected to the weight, which is vertically downward like this. And what is opposing the action of the weight is the normal reaction subjected on the solid S by the table. So in this case, so let me say that this is the table T. So in this case, the weight is the force referred to as the force exerted by the earth on the solid. Whereas here the normal reaction, let me say the following: the normal reaction is given by the force exerted by the table on the solid. So now here what I'm saying is that the normal reaction N is given by the force F exerted by the table on the solid. So I have named N to be the force exerted by the table on the solid. Okay, so now let me repeat the following. So here we have the table. So, and this is the solid. And we know that the normal reaction now is given by the force exerted by the table on the solid. Now here comes the principle of interaction. So because we have two bodies, which is the table and the solid S, we can say that because the table is exerting an action on the solid S, we consider there is another force which is said to be N prime. And notice that I have represented the force N prime at the point of contact A. So this is not the weight. If N prime is the weight, I should have represented N prime at the point G and not at the point A. So in this case, what is N prime? N prime is the force exerted by the solid on the table. If N prime is given by the weight, it will be the force exerted by the earth on the solid S. So this is the principle of interaction. The solid S will exert a force on the table T, and the table will exert a force on the solid S. Now what I will do here is I will state the principle of interaction. Now throughout the examples, the principle of interaction, it will be clarified more. So now let me state the statement of the principle of interaction, and let me say that when a body A exerts on body B a force, and this force is denoted by A on B, So this is the force exerted by A on B, and this is said to be the action. Then body B exerts a force on body A, which is denoted by, now this force is exerted by body B on body A, and this force is denoted by B on A, and this is said to be the reaction. So basically this is the statement of the principle of interaction. But now the thing is that what's the relation between FA on B and FB on F is that such that FA on B is equal to minus FB on A, or in other words we can say that the action and the reaction are opposite than FA on B and FB on A have. So previously we have seen this equation which give us the following, that they have the same line of action. So they have the same line of action, opposite direction, and the same magnitude. So this is basically the principle of interaction. Now interactions may be classified also into two types. It can be classified as an interaction at a distance or interaction by contact. So first let's consider the following example, which is considered to be interaction by contact. So we know what is meant by contact whenever the two bodies are in contact at a certain point. So let's consider example 1. Consider a solid S attached to the spring at A. So here we have the solid S and here we have the spring R. Both of them are in contact at the point A. They are telling me that the spring R exerts a force Fr on S. So the spring R is exerting a force Fr on S on the solid S. And we know that this force is the tension force. Okay, so because it's being represented at the point A and it is due to the spring on the solid S. Now because the spring R exerts a force on the solid S, according to the principle of interaction, the solid S will exert a force on the solid R. So because we have Fr on S, then according to the principle of interaction, we must have Fs on R. So I repeat what is meant by the principle of interaction. Because we have Fr on S, then we must have Fs on R. So how do we determine Fs on R? Fs on R will be at the point A, having the opposite, having same line of action but opposite direction and same magnitude. So let me repeat. What is meant by the principle of interaction? Here they are telling us that the spring R exerts a force Fr on S. So according to the principle of interaction, we must have another force which is given by Fs on R. So Fs on R will have the same point of application of Fr on S. So which is the point of contact A. Both forces have the same line of action, opposite direction and same magnitude. Now let's proceed. But here also I wanted to mention the following, that this force, which is Fs on R, is not the weight, because we know that the weight is represented from the center of gravity G. Now, are the bodies S and R in interaction? So we need to complete the following activity, which is we need to fill up the following spaces. So in the first one, they are telling us, are the bodies S and R in interaction, question mark. So we need to justify why the two bodies are at interactions. What are the two bodies that are involved in this problem? They are given by the spring R and the solid S. Or in other words, we need to state the principle of interaction. Then the statement of the principle of interaction is given by, or let me justify and say yes, since the spring R exerts on solid S a force Fr on S, which is said to be the action, then solid S exerts on spring R a force given by, so if this is Fr on S, which is the force exerted by R on S, then the force exerted by S on R will be given by Fs on R. So if this is the action, then this is the reaction. Okay, now how come do we know whether if this is the action or this is the reaction? It's not important. If we consider this force to be the action, then this force will be the reaction. If this force is considered to be the action, then this force will be considered to be the reaction. Now, what's the type of the interaction? So the interaction may be contact or at a distance. In this case, because both bodies are in contact at a point A, so this interaction is said to be interaction by contact. Because they are asking us about the name of this principle is known as the principle of interaction. Now they are asking us to write down the vector relation of this principle, and the vector relation, it means that an equation that includes vector, or in other words, we need to compare Fr on S and Fs on R. So as a title we will write, so in the case, so this equation is pretty similar to the condition of equilibrium. In the case of condition of equilibrium, we used to write as a title at equilibrium. In this case, we will write according to the principle of interaction. So we have that Fr on S is equal to minus Fs on R, which is the vector relation that we have written here in the principle of interaction, but here the bodies are given by R and S and not A and B. Then they are telling me to compare the magnitudes of the magnitude of the forces Fr on S and Fs on R. So in this case, we know how to deal with such type of equations. We drop down the vectors and we remove the minus sign. Then Fr on S is equal to Fs on R. So this is the first example that we have considered. Now let's consider another example. So in this example, we have a table and we have a solid. So we can consider that Ft on S is the force exerted by the table on the solid. Then according to the principle of interaction, because we have Ft on S, then we have another force which is given by Fs on T, and we need to answer the following questions. Okay, So what does Ft on S represent? It's the force exerted by the table on the solid, which represents the normal reaction. Then for this reason, according to the principle of interaction, we have another force given by Fs on T. But notice that this is not the weight, because the weight would have been represented from the center of gravity G. Then consider a solid S resting on a table. The solid S exerts a force Fs on T. So according to the principle of interaction, we must have another force given by Ft on S. Okay. Now, are the bodies S and R in interaction, or in other way, we need to state the principle of interaction? Then let me say yes. So for example, if you consider this one to be the action, then this is the reaction. If you consider this one to be the action, then this one will be the reaction. So let me consider this to be the action, then this will be considered as the reaction. So yes, since the table T exerts on solid S a force Ft on S, and this force is classified as the action, then the solid S, now we rewrite the statement, but instead of T it will be S, instead of S it will be T, instead Ft on S it will be Fs on T. If this is the action, this will be the reaction. Table T, a force given by Fs on T, which is said to be the reaction. Now, what's the type of interaction? Here we know that we have two types of interaction. They are given by interaction by contact or interaction at a distance. Since both bodies that are involved in interactions are given by the solid and the table, they are in contact at the point A. For this reason, this interaction is said to be interaction by contact. Then they are asking me about the name of this principle. We know that the name of this principle is given by the principle of interaction. Then they are telling me to write down the vector relation of this principle. Since we are concerned about this principle, then as a title, always we write according to the principle of interaction. So the two forces that are involved in this problem are given by Ft on S and Fs on T. Then the comparison or the vector relation between them is given by Ft on S is equal to minus Fs on T. Now we need to compare the magnitudes. So by comparing the magnitudes, simply we drop down the vectors and we remove the minus sign. So Ft on S is equal to Fs on T. So here let me give the following example. If Ft on S, which is the normal reaction, and we know how to calculate the normal reaction, which is 3 newtons, then in this case Fs on T is also given by 3 newtons. Now let's move to the final example, and in this case we are going to discuss interaction at a distance. So here, before I start reading this example 1 of section 18.2, here we have two bodies. They are given by the solid S and by the magnet. Then the force exerted by, so let me start by the magnet on the solid S. So notice that the magnet is pulling the solid toward the left. So this is Fm on S, the force exerted by the magnet on the solid S. So this is the magnetic force, because we have a force exerted by a body on another. Then according to the principle of interaction, we have another force which is given by, so we flip these two letters. So this force is given by Fs on M, which is the force exerted by the solid on the magnet. Okay, so let me repeat. Here we have two bodies that are at interaction. They are given by the solid and the magnet. So the first force that we can discuss is the force Fm on S. It's the force exerted by the magnet on the solid. Then according to the principle of interaction, we have another force given by Fs on M, which is the force exerted by the solid on the magnet. So let me start by the example. Consider a solid S attached to a string at A. S is being attracted by a magnet and it is in equilibrium. Then M exerts a force Fm on S, and so the solid S exerts a force Fs on M. Then if this force is said to be the action, then this force is said to be the reaction. Now in number 1 they are telling me, are the bodies S and M in interaction? Or in other words, we need to state the principle of interaction. So let me justify and say yes. Since the magnet M exerts on solid S a force given by Fm on S, if this force is classified as the action, then the force Fs on M, which is the force exerted by S on M, will be classified as the reaction. So this is the statement of the principle of interaction. Okay. Now in number 2 they are telling me what's the type of interaction. Now notice that in this case the solid S and the magnet, they interact with each other without being in contact. So this type of interaction is interaction at a distance. Now they are asking me about the name of this principle. We know that this is the principle of interaction. Now then they are telling me to write down the vector relation of this principle, or in other words, we need to compare these forces. So it's a relation that includes vectors, and we are talking about the principle of interaction. Then as a title we will write according to the principle of interaction. Then the two forces that are involved in this problem given by Fm on S and Fs on M, and they are related by a minus sign. Then in number 5 they are telling me to compare the magnitude of the forces Fm on S and Fs on M. So because we are interested in the magnitude and we know the vector relation, then simply in this case we drop down the vectors and we remove the minus sign. So we have that Fm on S is equal to Fs on M. So if we know the value of the magnetic force, we can determine the value of the force exerted by the solid on M. So this is it regarding the principle of interaction. Now let's consider the following exercises. Now exercise 14. In document 1, the solid S of center of gravity G and of mass M is equal to 0.8 kilograms. Is connected to the free extremity A of the spring, whose force constant is K is equal to 100 newtons per meter. The other extremity B of the spring is fixed to a support. Okay, so here we have the solid. The solid S is connected to the spring at the point A, and the spring is connected to the support at the point B. Now the system S spring is placed on an inclined plane. S is in equilibrium, so at any moment in this exercise we can use the condition of equilibrium. And the spring elongates by 4 centimeters. So the elongation of the spring is given by x is equal to 4 centimeters. But we know that centimeters is not the SI unit of length. In order to convert from centimeters to meters, we divide by 100. Now we neglect all friction and we take that G is equal to 10 newtons per kilogram. Now, before we refer to the exercises, let me consider an overall view of the exercise just based on the given. So notice that in this case we have the mass and we have a G. We can determine the weight. Now, let me say the following. So usually whenever we have the weight, because we have the condition of equilibrium, then we can deduce the tension. But in this case, we cannot deduce the tension. Now later on in the exercise, I will explain why. So the tension will be deduced not from the condition of equilibrium, but rather from Hooke's law. Okay, now throughout the exercise, we will discuss why. Then in number 1, they are telling me name the forces acting on the solid S. Because the solid S has a mass, then it will be subjected to the weight W. Because we have a spring, then it will be subjected to the tension T. Because we have a support, which is the inclined plane, it will be subjected to the normal reaction N. Now in number 2, they are telling me draw a diagram of these forces without a scale. So let me redraw the diagram. Now the spring itself on the diagram is not important. What is important for us is the inclined plane and the solid S. And let me say that this is the point A, and this is the point G, and this is the solid S. So the weight acting at the point G vertically downward like this. We have the tension along the spring, which is like this. And we have the normal reaction at the point of contact between the support and the solid S. Now previously, if you recall what I used to say, whenever we are representing forces without a scale, I used to say that it's important. The length of the forces itself is not important, but what is important for us to draw the forces with the same length. But in this case, this is not important for us because we are not drawing 2 vectors, we are drawing 3 vectors. So in this case, it's not important to draw the length of N to be equal to the length of T is equal to the length of W. This is not important anymore. But if we are representing forces on a solid S only consisting of 2 vectors, this is extremely important. Now this is it for number 2. Now in number 3, determine the magnitude each of the force. 3.1 exerted by Earth on the solid. So we have 3 forces: the weight, the tension, the normal reaction. The force exerted by the Earth on the solid is referred to the weight. So we need to determine the magnitude of this force. So the weight is equal to M multiplied by G. We have the value of M, which is given by 0.8. And we have the value of G, which is given by 10. Plugging this on the calculator, then the value of the weight is given by 8. Since both this and this are expressed in the SI, so the value of W will be in the SI, which is in newtons. Okay, now in 3.2 they are telling me F2 exerted by the spring on the solid. So in this case we need to read the question like this: determine the magnitude of the force exerted by the spring on the solid. We have already discussed the weight. We are left with the tension and the normal reaction. The tension is the force referred to the force exerted by the spring on the solid. The normal is the force exerted by the support on the solid S. So because they are telling me exerted by the spring on the solid, so the force due to the spring is the tension, we need to determine the magnitude of the tension. Now the magnitude of the tension can be determined using Hooke's law. Then let me write as a title apply Hooke's law. So Hooke's law is given by T is equal to K multiplied by X. Here, because the elongation is denoted by 4 centimeters, we are free to write X or delta L, but from the early beginning I have denoted the elongation to be X and not delta L, so we will fix this notation. Now the value of K is given by 100, and the value of X is given by 0.04. Now plugging this on the calculator, the value of T is given by 4. Since K and X are expressed in the SI, so the value of T will be in the SI, which is in newtons, then T is equal to 4 in newtons. Now let's recall that why we have calculated the tension using Hooke's law and not the condition of equilibrium, although we know the magnitude of the weight. So the thing is that now if we refer to this diagram and we need to write the condition of equilibrium, so as a title we will write at equilibrium. So on the left hand side we write the different forces acting on the solid S given by the weight, the normal and the tension, and in this case we will say that W plus N plus the tension is equal to 0 vector. So in this case here it's clear that we have 3 forces that are sharing the magnitudes. So we have another term that is present, which is the normal reaction, okay? So we cannot say that if the weight is equal to 80 newtons, that the tension is equal to 80 newtons due to the presence of the normal reaction. Okay, so for this reason we didn't use the condition of equilibrium, simply because how many forces acting on the solid S? 3 forces and not only 2 forces. Okay, so in this case we need to apply Hooke's law and not the condition of equilibrium. Okay, so always whenever we are free to choose if we have the condition of equilibrium and or let me say the following: if we have 2 ways to choose whether the condition of equilibrium or Hooke's law, so as a first choice we always use Hooke's law, then the second choice will be the condition of equilibrium. So one should always keep this in mind. Now in number 4 they are telling me the solid S exerts a force F3 of magnitude F3 on the extremity of A of the spring. So let's read this statement carefully. They are telling us the solid S exert a force F3 of magnitude F3 on the extremity of A on the spring. So let me refer to the following diagram because we have the spring and we have the solid. So it is the force F3 exerted by the solid on the spring. So it must be like this. This is the force F3, which is the force exerted by the solid on the spring. Okay, before we refer to part 4, let me make something here. Now in number 3 they told us determine the magnitude of the force F1 exerted by the earth on the solid. So here let me say that F1, which is the weight, which is equal to 80 newtons, okay? Or it's okay. And let me say it here, F1 is equal to the weight, which is equal to 80 newtons. Or between the brackets here, we can say that this is the force F1. And this is the force F2. This is important. Now I repeat, the solid S exerts a force F3 of magnitude F3 on the extremity of A of the spring. So this is the force F3. Give the statement of the principle of interaction. So here we just need to state the principle. So what is the statement of the principle of interaction? It's given by when a body A so here the body A is given by the solid S, so this is the first body, and the second body, for example, can be the spring, which is R. So when a body S exerts on body R, which is the spring, a force, so this force is said to be the force F3 given by the action. Here we could have said that Fs on R, but since they are referring to this force to be the force F3, so it's okay to keep it like this. Then body given by R, so now we flip the letters. Then body R exerts on body S, and here we are referring to the force exerted by R on S. So what is the force exerted by R on S? So if R is the spring and N is the solid, then the force exerted by R on S is the tension force, which is like this, and here the tension force is noted by the force F2. Okay, so this is the force F2, and here because we have referred to the force the force S on R, which is the force F3, we didn't use the notation Fs on R. So here we are not going to use the notation Fr on S, however we are going to use the force, the notation which is given by the force F2, and this is said to be the reaction. So this is the statement of the statement of the principle of interaction. Now they are telling us to compare then F3 and F2, so we need to compare two quantities that are vectorial quantities. Then we are going to say according to the principle of interaction, so these are the two forces that are involved in the problem, then they are equal to each other up to a minus sign. So notice that here part 4 consists of 3 parts. We are done with the first part, the second part. So this is the first part. We are done with it. This is the second part, we are done with it. And as for the final part, we need to deduce the magnitude of F3. And by deduce, it means that we need this the previous part. In the previous part, we have determined the vector relation between F2 and F3. Now we need to determine the magnitude of F3. So let me say in magnitude, that F2 is equal to F3. So in this case, we drop down the vector quantities and we remove the minus sign. Now recall that F2 is the force exerted by the spring on the solid, and we have that the force F2, which is equal to the tension, is equal to 4 newtons. So, but we know that the value of F2 is equal to 4 newtons, then the value of F3 is equal to 4 newtons as well. Now let me move to the other exercise, which is exercise number 15. Now in order to determine the force constant stiffness K1 of inelastic spring, So the aim of this exercise is to determine the value of K1, and recall that always and forever the value of K1 is determined using Hooke's law of an elastic spring R1. Let me write the properties of R1. Then the value of K1 is unknown, and the value of the initial length, so this is the free length. Knowing that centimeters is not the SI unit of length, in order to convert from centimeters to meters, we divide by 100. So this is equal to 0.2 meters. We consider the system of document 1, they mentioned document 1, now we can use it. In the system, the extremity A of R1 is connected to a fixed support. So notice that the spring R1 has two extremities, the extremity A and the extremity O. A is connected to a fixed support, so this is okay. The other extremity is connected to O. Okay. So one of the extremities is connected to A and one of the extremities is connected to O. The other extremity is connected, to another spring R2. So here we have R2 that also consists of two extremities. One of the extremities of R2 is connected to O. So let me say that here we have another spring R2 given by K2 is equal to 100 Newton per meter. And of free length given by L2 is equal to 30 centimeters. Knowing that centimeters is not a unit of length, in order to convert from centimeters to meters, we divide by 100. Then 30 divided by 100, this is equal to 0.3 meters. So these lengths are the free lengths. The other extremity B of R2 is connected to another fixed support. Then here in this case, the system formed of R1 and R2 is at rest. Then recall that at rest means it is at equilibrium. Now in number 1 they are telling me, referring to document 1, calculate the length L1 prime of R1. So here this is very important that they are telling me referring to document 1. So no need to use any formula or any law. So simply we need to refer to the document. Now what does L1 prime represent? L1 prime is the length of the spring which is given by R1. So notice that if the total length from A to B is given by 65 centimeters, and we know that L2 prime is 35 centimeters corresponding from O to B, what is the length AO? So in other words, what is the number that must be added to 35 to give us 65? So in this case, L1 prime is given by 65 minus 35, which is equal to 30. Since this and this are expressed in centimeters, so the value of L1 prime is centimeters. Knowing that centimeters is not the SI unit of length, in order to convert from centimeters to meters, we divide by 100. Then 30 divided by 100, this is equal to 0.3 meters. So this is equal to 0.3 meters. This is equal also to 0.35 meters if we divide by 100, and this is equal to 0.65 meters. Now in 2.1, show that the springs are elongated. What is meant by the spring is elongated? The spring to be elongated. So we know that the spring has a free length, and if the spring elongates, the condition here that the new length, which is L prime or L, must be greater than L0. So in this case, if we compare L and L0, this is sufficient to prove that the spring is elongated. So as for the spring R1, we know that the free length of the spring is given by L1, which is equal to 0.2 meters. And the final length of the spring, which is denoted here, which is given by 0.3 meters. So in order to indicate whether the spring is elongated or compressed, it is sufficient to compare the final length with the initial length, knowing that this is the initial length, which is the free length. So in this case, it's obvious that L1 prime is greater than L1. So because the final length is greater than the initial length, so the spring is elongated. However, if the final length is less than L1, so the spring is compressed. So let me say since L1 prime is greater than L1, then the spring R1 is elongated. Now as for the spring R2, we know that the initial length of L2 is given by 0.3 meters. And its final length extracted from document 1 is given by 0.35 meters. Now we need to compare both lengths, knowing that the final length is greater than the initial length. Because the final length is greater than the initial length, which means that the spring is elongated. Okay, so recall that if L2 is greater than L2 prime, so the spring is compressed. So what is meant by compress? So the free length of the spring will be like this. By compressed, it is mean like this, okay? So as if a mass M is placed on the spring like this. So in this case L2 prime and this is L2, so L2 prime will be less than L2, okay? Let me make some space here. Now in 2.2 they are telling me calculate the elongation delta L1 of R1 and delta L2 of R2. Then delta L1, so delta means the difference, which is equal to L1 prime minus L1, which is equal to 0.3 minus 0.2, which is this one. Since this is expressed in meters and this is in meters, then delta L1 will be in meters, so this is equal to 0.1 meters. Now as for delta L2, which is equal to L2 final minus L2, now here by prime, it means the final, which is equal to 0.35 minus 0.3, so this is equal to 0.05 meters. Then delta L2 is equal to 0.05 meters. Now here in 2.3 they are telling me R1 and R2 are in interaction. They are telling me that both springs are in interaction. So then they are asking me why. So by why, it means that we need to state the principle of interaction or the statement of interaction. And this is because R1 is exerting a force of N on R2, which is given by this one. So the spring R1 is pulling the force R2 toward the left. So this is the force F exerted by R1 on R2. So according to the principle of interaction, the spring R2 will exert a force given by F R2 on R1. Then let me say, yes, since the spring R1 exerts on spring R2 a force given by F R1 on R2, and this is said to be the action, then the spring R2 exerts, so now we flip them, that this is R2 and this is R1, a force given by R1, on R1, given by FR2 on R1, which is said to be the reaction. Okay, so this is the principle of interaction. Now in number 3, they are telling me write down the vector relation between the two forces T1 exerted by R1 on R2. So here, the force exerted by R1 on R2 is denoted to be the tension T1, and the other one is denoted the tension T2. So in this case, no need to refer anymore to the forces FR1 on R2 or R2 on R1. Simply we can refer to them as the tension T1 or the tension T2. So here the vector relation that we are concerned about, we don't think about the condition of equilibrium because we are talking about the principle of interaction. So we think about the vector relation due to the principle of interaction. So let me write here according to the principle of interaction as a title. Then the two forces that we are interested in are given by T1 and T2. So this is T1 and this is T2. Then T1 is equal to minus T2. And these are actually the tension forces. And T1 and T2 can be calculated using Hooke's law. Now in number 4, they are telling me calculate the magnitude of T2 of the force T2. So let's stick to this part of this question. Now T2 can be calculated directly using Hooke's law because we know the value of K2 and we know the values of delta L1 and delta L2 that we have pre-calculated. Let me write here that delta L2 that we have erased is given by 0.05 meters, and delta L1 that we have calculated in number 2.2 is given by 0.1 meters. Then let me say apply Hooke's law. So here, because we have two springs, then I will say apply Hooke's law to R2. And Hooke's law is given by T is equal to K delta L. So we are using delta L and not X because everything here is denoted by delta L. We are interested in determining the tension T2 of the spring R2 having stiffness K2 and elongation 2. So K2 is given by 100 and delta L2 is given by 0.05. Plugging this on the calculator, then the value of T2 is given by 5. Since everything is expressed in the SI, so the value of T2 will be in the SI, which is in newtons. Then T2 is equal to 5 newtons. Now in the same exercise, they are telling me to deduce the magnitude of T1, and by deduce it means that we notice the previous part. In the previous part, we have determined the value of T2, and we know the vector relation between T1 and T2. So now we will say in magnitude. Now we drop down the vectors and we remove the minus sign, so T1 is equal to T2. But we know that the value of T2 is equal to 5 newtons. Then in this case, the value of T1 will be equal to 5 newtons. So here, let me say that also we have that the value of T1 is equal to 5 newtons. Now finally, in part 5, they are telling me to find the value of K. This is straightforward using Hooke's law, because now we know the value of T1 and we know the value of delta L1, so we can determine K1. Then let me say apply Hooke's law. So here, because we have two springs, let me say apply Hooke's law to R1. And this is given by T is equal to K multiplied by delta L. We are interested in determining the value of K, constructing the triangle of this formula, putting our hand over K, then K1 is equal to T1 divided by delta L1 Now T1 is given by 5 and delta L1 is given by 0.1. Plugging this on the calculator, then the value of K1 is given by 50. Since both T1 and delta L1 are expressed in the SI, so the value of K1 will be expressed in the SI, which is in newtons per meter. Then K1 is equal to 50 newtons per meter. Now notice that K1 has a value of 50 newtons per meter, then it means that in order to elongate or compress the spring here by 1 meter, we need to exert a force of worth of 50 newtons per meter. As for the spring R2, which is given by 100, so in order to compress or elongate the spring by 1 meter, we need to exert a force which is given by 100 newtons, which is the double of this. For this reason, delta L2 will be the half of this, because this spring is more stiff than this spring. Okay, so when the spring R1 elongates by 0.1 meters, the spring K2 will be elongated only by 0.05 meters because K2 is more stiff than K1. And now let me move to the final exercise, which is exercise number 16. They are telling me an iron ball A of mass M is equal to 200 grams. Knowing that the grams is not the SI unit of mass, in order to convert from grams to kilograms, we divide by 1000. And we have that G is equal to 10 newtons per kilogram, which means that we are performing this experiment on the surface of the Earth. The moment we have M and G, we can determine the weight independent whether the ball is at equilibrium or no. Number 1, the ball A is in equilibrium, document 1. They mentioned document 1, then now we use document 1, and we are not allowed to use document 2. Give the name of the forces of the two forces acting on A. So because it has a mass, then it will be subjected to the weight W. And because we have string, it will be subjected to the tension T. Now, if you complete the question, they are telling us tell for each of these forces whether it's a contact force or force acting at a distance. We know that the only three forces act at the distance are given by the weight, the electric, and the magnetic. So this is acting at a distance. And all other forces are classified as contact forces, and in particular the tension T. Now here, look at the following. Because the only forces acting on the solid S are two forces given by the weight and the tension, because we have M and G, we can determine W. Knowing W, we can determine T. But suppose that for some reason we have another force which is given by the normal reaction, we cannot say anymore that because we have the weight we can deduce T because there is another existing force. Suppose, for example, we have the normal, but in this case we don't have the normal. And indeed, in number 2, they are telling me to write down the vector relation between these two forces. We have either the principle of interaction or the condition of equilibrium. In some sense they are similar, but here because they didn't mention anything about the interaction, so we'll only use the condition of equilibrium. So as a title, we will write at equilibrium. On the left hand side of this equation, we write the different forces acting on the solid A given by the weight and the tension. And on the right hand side, we write the zero vector corresponding for the condition of equilibrium. Dragging T to the right hand side, we have that W is equal to minus T. Now in number 3, calculate the value of each of these two forces. The weight can be directly calculated by M multiplied by G, which is equal to 0.2 multiplied by 10, which is equal to 2. Everything is expressed in the SI, so the value of W will be in the SI, which is in newtons. Then the weight is equal to 2 newtons. Now we need to deduce the magnitude of the tension, and this can be deduced from this equation. Weight is equal to minus the tension. So we will say in magnitude that the weight is equal to the tension. We drop down the vectors and we remove the minus sign. But we know that the value of the weight is equal to 2 newtons, then the value of the tension is equal to 2 newtons. Now in number 2, a magnet as an approach to A attracts it by force F, document 2. Now they mention document 2, now we are allowed to use it. So here, okay, F is the force due to the magnet, so this is the magnetic force. Now, so F is the force exerted by the magnet on A, so this is the force F. Now they are telling me the ball exerts on the magnet a force F prime. So F prime, it is the force exerted by the ball on the magnet, which is this force F prime. So F is the force exerted by the magnet on the ball, whereas F prime is the force exerted by the ball on the magnet. Now in number 1, they are telling me F and F prime verify a certain principle. Give the name of this principle. So this is simply the principle of interaction. One point to state this principle. So let's state it. When body A, or let me say one body Sn. So here it's not important. We can consider this one to be the action and this is the reaction, or vice versa. One body Sn exerts on body, so the other body is body a force. So it is the force exerted by Sn on A. So this is it, the force F, which is said to be the action. Then body, now we flip them. Then body A exerts a force on body Sn, which is said to be the force F prime, and this is the reaction. Okay, so this is the principle, the statement of the principle of interaction. Then in 1.3, write down the vector relation between F and F prime. Since these are related to each other and we are talking about the principle of interaction, then we will write as a title according to the principle of interaction. So what are the two forces that are involved in this interaction? They are given by F and F prime. So we have that F vector is equal to minus F prime vector. Now in number 2, they are telling me redraw document 2 and showing it without a scale the three forces acting on A. So first let's draw it. So this is the support, this is the vertical, this is the suspended string, and this is the solid A like this. Now here in this case, how many forces we have? We have F prime, we also have the weight, and we have the tension. Recall that the line of action of the tension is always along the string and the point of application is the point of contact. So this is the tension. But if you notice that they are telling me and show on it only the three forces acting on A. So here we have four forces, three of them acting on A and one of them is acted on the magnet. So we will only represent the weight, the magnetic force, and the tension. So this is the weight, this is the magnetic, and this is the tension. Now recall that here in this case they told me show on it without a scale, so the length of the vector is not important. Now because we have 3 vectors and not 2 vectors, it's not important at all to draw the length of these vectors to be the same. Okay, so this is not important. This can be 2, this can be 3, this can be 4, etc. The length of the vectors is not important at all. Okay, so that's it for me in this video, guys. See you soon in a new one.